but keep in mind that our quantum results come from a quantum amplification of randomized algorithm. So we're going to be seeing a bit of both. So what is our model of distributed computing? So in our model, we represent a network with n computing nodes by a graph with the same number of nodes. And they're going to be talking to their neighbors through communication channels, which are represented by the edges of the graph. And to break symmetries, they also each have assigned a private identifier, which is taken in poly n, and you can assume that they are chosen by an adversary, those identifiers. So now it's time to define what is the CONGEST model. But first, we have to go back to the most basic model, which is the local model. So in the local model, this network graph, the algorithms, they work in synchronous rounds, and they have no error. No error in communication, no error in computation. And so during one round, each node is going to be able to communicate what they want with their neighbors, and then perform some private computation before moving on to the next round. So to measure the efficiency of an algorithm, we are just going to count the rounds. How many rounds does it take to solve the task at hand with this algorithm? So the CONGEST model is exactly the same as the local model, with one more constraint. This constraint is that the communication through each edge is going to be limited. So in one round, we say that at most big O log n of bits can travel an edge. So here on this drawing, you can see a visual representation of this congestion, of this bandwidth constraint. So let's say that the central node has d neighbors, and it knows its identifiers. So it would want to inform its bottom neighbor of all these identifiers. In the local model, it can just forward all of these identifiers in one round because there is no bandwidth constraint. But with a bandwidth constraint, as I said before, an identifier is taken in poly n, so it takes up as a finite factor of log n bits to represent. So it would take d rounds in the CONGEST model to forward d identifiers. So this is why the CONGEST model is much less powerful than the local model. So what we're going to be talking about is cycle detection. So cycle detection is, in a formal manner, it is a variant of the H-finesse property. So what does it mean to decide the H-finesse property with one-sided error? So let H be a fixed connected graph. Then if the network contains no copy of H, all the nodes must accept in the network. Otherwise, if there is a copy of H in the network, then with probably 2/3, at least one node should reject. So you can see a visual representation. Once again, this is an example for triangle detection. So on the left drawing, there is no triangle. So all nodes accept. But on the right side, there is a triangle on the bottom. So at least one node should reject. It doesn't matter if the node is part of the actual triangle or not. We just want one node in the network to reject. So why are we interested in the H-finesse property in the CONGEST model? Well, as I said before, the local model is pretty powerful. Actually, its name comes from the fact that it's a measure of locality. Without a bandwidth, without a limitation of communication during rounds, in k rounds, a node can learn about all its neighborhood at distance k. So that's why H-finesse is trivial in the local model. It just takes a number of rounds that is equal to at most to the size of the subgraph H. But in the CONGEST model, with a limitation on with the bandwidth limitation, it becomes much more interesting. And in fact, there even exists gadget graphs H that could take up to a nearly quadratic number of rounds to solve in the CONGEST model. So now, why cycles specifically? Well, we saw that the H-finesse property was closely linked to the amount of information that has to travel through the graph in the CONGEST model. And it can vary, the difficulty can depend based on the graph H. So for the simplest kind of graph, the trees, it is as trivial in the CONGEST model as it is in the local model. So what about the next simplest kind of graph, cycles? Well, it is still an open question, so that's why we are still studying it. And why is it interesting to solve it quantumly? Well, of course, in a distributed manner, we would like to know if there could exist a faster quantum algorithm in the same distributed models, but also quantumly, it has its interest because trying to figure out the quantum possibilities in distributed models can help us give us intuition about quantum physics. And also, it happens that the H-freeness property is particularly well suited for quantum speedups, as the state of the art shows, where the field has already seen quantum speedups for triangle detection, for clique detection, and even for force cycle detection. So that's why we were interested in expanding those results to all kind of cycles. One thing I should mention is what is the definition of the quantum congest model. It's basically the same, except we also, in addition to classical bits, we allow the nodes to prepare quantum bits, qubits. And it is important to know that pre-entanglement is not allowed. The nodes have to prepare their qubits themselves and exchange them between them. So now for the state of the art. This was the state of the art of cycle freeness in the randomized and quantum congest model before our work. So you can see on the top line that the triangle is a bit of a particular case with no lower bounds. But for bigger odd cycles, the question is entirely solved. It is linear in the size of the network. It is a linear round complexity. For force cycles, the question is also solved as well in the randomized setting. It needs the square root of n rounds to solve. And as I mentioned before, there is a quantum algorithm solving a force cycle already. There was one. And on the bottom line, you can see that other even cycles are a bit more of an open question with a lower bound that does not match the best general upper bound. And now, here is the gaps that our work allowed to fill. So first of all, on the randomized, a big part of our work, you can see on the randomized size, was to improve the upper bound, the general upper bound on even cycle detection. But I'm not going to cover that today, so let's talk directly about the quantum side of things. So you can see basically that all the randomized results in the state of the art now have a quantum equivalent. How does this work? Well, we proved two kinds of bounds, new upper bounds and new lower bounds. The lower bounds, it was very straightforward. It was exactly as in the randomized setting. So it comes from a reduction from the set disjointness problem in the two-party communication complexity model. But instead of plugging the randomized communication complexity, we plugged the quantum communication complexity, and it yielded directly the same lower bounds, except that they are quadratically smaller. For the upper bound, as I mentioned in the title page, it revolves around quantumly amplifying the randomized algorithms that are already existing. So that's why the upper bounds are also quadratically smaller in the quantum setting compared to the randomized setting. And that's why also our new upper bound for the even cycle detection yielded directly a pretty efficient quantum algorithm for even cycle detection. So now it is time to see how it works, but we have to start with the classical side to see how we can amplify it later on. So we're going to see a pretty straightforward classical algorithm. It is optimal for odd cycles. It works also for even cycle, but it is not as good as the randomized algorithm we devised. So there is this technique called the color coding technique that can test if a node U is in a K-cycle in a constant number of rounds. So we call it BFS of U because the idea is going to be to flood the graph around the node U with U's identifier, meaning that only its identifier is going to be traveling the graph at a finite distance. So that's why it's a finite number of rounds. So the idea is that now that we know how to efficiently test if one node is in a K-cycle, how to search for any cycle in the graph, well, it is to test every node at once. So launch a search in parallel for every node. So of course, it's not one identifier that can travel the graph, but all of the identifiers. So the complexity gets multiplied by the size of the network. And so that's why launching the color coding technique from testing all nodes at once gives a linear complexity, which is once again optimal for odd cycles. But how can we hope to beat that quantumly? Well, you might have a good intuition that basically what I said is that we are searching for a node in a K-cycle in the network. So how to quantumly efficiently search for things? We can use a Grover search, and it happens that the distributed Grover search exists and has already yielded many results in the quantum congest model. So let's talk about this distributed version of the Grover search. So we have a set X in which we want to find marked items in a set M. And the idea is just going to be to centralize the search through one designated node in the network, which is a node V, which is going to be performing the Grover search as if it was in a sequential model, in a centralized model. So it's going to sample in X, but it does so privately. So it does not cost any rounds to do that. And of course, we assume that there is a probability of sampling a marked node if marked nodes exist. And then there's going to be a checking procedure, which is going to be a quantum oracle, but to check whether nodes are marked or not. But maybe this designated node, because we are in a distributed setting, this distributed node does not have all the information it needs to in order to do this quantum oracle. So this checking procedure should be done distributively. So it's going to cost us some rounds, and we say our rounds here. So if these conditions are assembled, then the node V can perform a Grover search to decide if there exist marked items, and it's going to cost this number of rounds that you can see on the screen. So let's explore what each term means. So you have the big D here, which accounts for the diameter of the network. So this is the time it takes to designate a node V that is going to perform the Grover search. And then you have square root of 1 over epsilon. So you are used to this factor. It is the number of iterations that the Grover search needs. So the number of time it needs to repeat the sample and checking procedure. And then our rounds, which is the cost of both the sampling and checking procedure, because the sampling procedure is done privately, so it costs no rounds. But this complexity is not yet all that satisfying, because the diameter of the network might be linear in the size of the network. It might be n itself. And if we want a faster quantum algorithm, we need a sublinear round complexity. But luckily for us, for the H-finesse property itself, one can always assume that the diameter is polylogarithmic in the size of the network. So this diameter parameter can be hidden in the tilde in the round complexity. So now we're going to try to perform this Grover search and apply it on our cycle detection algorithm. So the support X is going to be the set of identifiers in the network. And of course, the marked item is going to be a node, an identifier of a node that is in a K cycle. So if there exists a node in a K cycle, there is probability at least 1 over n of sampling it. And the checking procedure, we want to check if one sampled node is in a K cycle. So we can just use our color coding technique, and it runs in a constant number of rounds, as mentioned before. So plugging this into the Grover search theorem, you can see that it directly yields the D plus square root of n round complexity, and we can get rid of this diameter parameter thanks to the diameter reduction theorem and have our square root of n round complexity. But actually there is a big problem with what I just said, and what is it? The big problem is, can the designated node V actually sample in the support of all identifiers in the graph? If identifiers were taken between 1 and n, the nodes in the network, they know the value of n, so it could sample a number at random, and everything would work just fine. But I said, when defining the model, I said that the identifiers were private, and they were taken in poly n, and they were chosen by an adversary. So at the beginning, the node V has no idea of which identifiers are actually in the network. So we could maybe say that it could learn all of them through communication in a distributed setting. But then again, if the designated node ends up being pretty isolated in the network, then it could take up to n rounds for it to learn all of the identifiers in the network. So this is not viable, as we once again want a sublinear round complexity. So we need to be smarter than that. So let's take a step back and summarize the situation. We have a neat classical algorithm, color coding, that can test in a constant number of rounds whether any node U is in a K-cycle or not. So classically, the best that one can hope to do with that, maybe, is to test every node in parallel. Quantumly, we can search for things quadratically faster, thanks to Grover. So this is the idea. And the distributed Grover search already exists, which revolves around a centralized sampling by a node V and a distributed checking. But we just saw that a centralized sampling does not work because the node V has no idea of all the identifiers in the network. So maybe the idea could be to have some kind of local sampling, where a node is going to decide by itself if it's if it is sampled or not. So what would this look like? Well, this is a classical solution. Actually, we're going to classically modify the color coding technique, where each node is going to select itself with probability 1 over n. And then the selected node are going to be the tested node for the color coding procedure. So what is the effect of that? Well, of course, if there exists a node in a K-cycle, it has only probability 1 over n of being selected, so the success probability is now 1 over n. But what about the round complexity? Well, the number of nodes expected to be selected is also divided by n, because of this probability of being selected. So the round complexity also gets divided by n, because there are that much less identifiers traveling through the graph, and we end up with a constant round complexity. So we have a new classical algorithm that has a very low round complexity, but also a very low success probability. So maybe this is now the time to launch a quantum amplification and to quantumly amplify this Monte Carlo algorithm. So we do it in a distributed manner. So with a distributed randomized algorithm deciding property P in T rounds with one-sided success probability epsilon. Epsilon is supposed to be small. Then there is a quantum algorithm B that decides the same property with this round complexity by applying a Grover search to amplify this Monte Carlo algorithm. So applying this to our setting, how does this work? So we start from the classical algorithm, but not the original one, or modified classical color coding technique, which involves local sampling with low success probability 1 over n and constant probability. And then we perform the Monte Carlo amplification of this algorithm. So the success probability gets boosted back to something very close to 1, and the complexity, the round complexity, is only increased up to square root of n. There is a diameter factor, but thanks to the diameter reduction technique, we can get rid of it and achieve the square root of n round complexity. So so here is a reminder of the state of the art as of today. So you can see that, except for triangles, as I said before, the classical and quantum settings are now at the exact same point, with every round complexity in the quantum settings being quadratically smaller than its classical counterpart. But there are two big open questions remaining, of course. What is the true complexity of triangle detection? There is still no lower bound. And you can see that the gap between the lower and upper bound for even cycle is also still pretty big, both in the quantum and the classical setting. Another question that might arise is, with tools like distributed Grover and our Monte Carlo amplification technique, can we expect that for all graphs H, the quantum complexity of H finesse is actually quadratically smaller than the round complexity of H finesse? So this is it for my talk. Thank you for listening.
So what do you expect is the correct answer for like triangle and even cycles? Or
For the correct answer for the first or second question?
for both the triangle and even cycles.
Okay, for triangles, triangles are a very particular case on which I have not worked and thought about, so I wouldn't be able to have an educated guess on this. For even cycles, this is actually what I've been mainly working on since I began my research. I've tried several times to beat the n to the 1 minus 1 over k round complexity. As of today, I have no idea how to do so. And like, we aimed at this round complexity because the previous work on it kind of hinted that this could be something to be hoped as a round complexity. And it seems like today there is a lack of ideas as how to beat that. So it's a real question whether maybe this upper bound is the true complexity of the problem.
Okay, thank you.
Hi, thanks for the talk. Would there be any possibility that you can get a better than quadratic improvement from the random to the quadratic case?
So, sorry, can you
better than quadratic, would that be possible, do you think?
Well, it's hard to imagine because Grover search, in a sense that is searching for a marked element, is optimal, as we know, quantumly. So, if based on this situation where we try to quantumly amplify classical techniques, it's hard to imagine that we could beat a quadratic speedup. And as of today, in the quantum congest model, actually all the quantum speedups come from this distributed Grover search. So actually, is there any kind of quantum advantage of other nature rather than just quantumly search for things is a real question in the quantum congest model. So,
that's what I was asking, like whether there's other non-Grover techniques for this.
Okay, as of today, there is not. Yeah.
Okay, would you think that it's a bit too unstructured for there to be non-Grover techniques?
Well, because the congest model adding this bandwidth constraint basically turns distributed computing into an application of communication complexity. So in this sense, it makes sense that the quantum advantage comes from searching for things optimally. But in the local model, although it is still pretty young, there are quantum advantages that do not rely on Grover search, that rely on non-locality. So maybe one day we could hope to see that in the quantum congest model, but even in the local model, it has not appeared in natural problems, only on problems tailored specifically to show quantum advantages. So that's a pretty hard bet to make.
Thank you.